this was a time when life nearly vanished from Earth. A slow death unfolding across an entire world. Around 252 million years ago, a catastrophic biological disaster, known as the Great Dying, swept across the planet. Within a relatively brief interval in geological history, nearly 90% of marine species and more than 70% of terrestrial animals disappeared. The oceans became suffocating, the climate descended into chaos, and ecosystems collapsed on a global scale. What makes this event truly terrifying is not only the number of species lost, but the speed at which an entire living planet could be driven to the brink of extinction. What exactly happened during this extraordinary chapter of Earth's history? Right at the Permian-Triassic boundary, the sedimentary layers form what can only be described as an almost perfectly preserved geological crime scene. Scientists turn to zircon minerals, remarkably durable crystals that typically form in magma. Zircon contains uranium, a radioactive element that decays into lead over time. Using uranium lead dating, researchers can determine the age of volcanic ash layers embedded within the sediments with extraordinary precision. What is truly shocking lies in the chemical fingerprints. Across the globe, researchers have documented a dramatic drop in carbon isotope values. This event is known as a carbon isotope excursion. Alongside this carbon shift are widespread signs of oceanic oxygen depletion. In rock layers from the same interval, scientists frequently find pyrite framboids, tiny spherical iron sulfide crystals that typically form in low oxygen environments. Additional biomarkers point to the presence of sulfur-loving photosynthetic bacteria, organisms that thrive in waters rich in hydrogen sulfide. Numerous genera of brachiopods and ammonoids decline dramatically. On land, the fossil record tells the same story of profound crisis. Since coal forms from the accumulation of plant material in wet environments, its disappearance suggests that forest ecosystems collapsed on a massive scale. All of this evidence, zircon ages, carbon isotope anomalies, signs of anoxia, and the fossil disappearances, converges on a single conclusion. Earth experienced a planetary-scale ecological shock. Instead, there is a chain of chemical and climatic transformations spreading across the planet, recorded in meticulous detail within each layer of rock. What triggered such a profound shift? Where did the immense volumes of carbon come from? To uncover the cause, we must look northward, toward one of the largest volcanic regions ever to exist in Earth's history, where vast rivers of lava reshaped the planet's climate in ways that would prove nearly irreversible. The Siberian traps were not a single volcano. They were a large igneous province, a vast magmatic province where lava erupted continuously through thousands of fissures stretching for hundreds of kilometers. Geological studies indicate that this eruptive activity lasted for roughly 1 million years. If all that molten rock were spread across the surface of the United States, it could form a layer more than 300 meters thick. But the real danger lay in the gases as magma rose through Earth's crust. Even more critically, when the lava intruded into layers of organic-rich sediments and coal deposits, the amount of carbon burned and released into the atmosphere may have surged dramatically. Uranium-lead zircon dating from volcanic ash layers shows that the main eruptive phase coincided closely with the Permian-Triassic boundary. Halogens had the potential to damage the ozone layer, increasing UV radiation at the surface. Meanwhile, accumulating carbon dioxide intensified the greenhouse effect, warming the oceans and reducing the ability of seawater to dissolve oxygen. This combination triggered a chain reaction. When oxygen levels dropped below a critical threshold, anaerobic bacteria proliferated and produced hydrogen sulfide, a toxic gas. Evidence of this process is found in pyrite framboids and sulfur bacteria biomarkers preserved in sediments from the same period. Geophysical studies suggest that much of the greenhouse gas release may have come from subsurface magma, sills, where magma intruded into carbon-rich sediments. The release of methane from sediments, and possibly from methane hydrates on the seafloor, amplified the warming process. The overall ecological upheaval lasted about 1 million years, but the most catastrophic phase unfolded over a geologically brief interval, almost instantaneous on Earth's timescale. When greenhouse gases rise rapidly, when temperatures increase by several degrees in a short span, when oceans lose oxygen, the entire ecological network can fracture. And to understand how the climate system crossed that threshold, we must look deeper into the cascading feedbacks that followed. When carbon dioxide increased, oceans warmed, oxygen vanished, and a hydrogen sulfide-rich world began to emerge. When the Siberian traps began releasing trillions of tons of greenhouse gases into the atmosphere, Earth did not collapse instantly. Paleoclimate models suggest that dissolved oxygen levels may have fallen below the threshold required to sustain many complex marine ecosystems. In both shallow and deep marine rocks, scientists have found pyrite framboids, tiny spherical clusters of iron sulfide crystals. Their size and distribution indicate prolonged low oxygen conditions As oxygen levels dropped to extremely low levels, another group of microorganisms rose to dominance. Sulfate, reducing bacteria. Instead of relying on oxygen, they used sulfate dissolved in seawater and produced hydrogen sulfide, a toxic gas with the smell of rotten eggs. Evidence for eoxinia, an ocean enriched in hydrogen sulfide, has been discovered in chemical biomarkers from sulfur bacteria preserved in late Permian sediments. At the same time, sulfur isotope anomalies in the geologic record show that the global sulfur cycle had been profoundly disrupted. As the oceans warmed, seafloor sediments containing methane hydrates, ice-like structures stable under high pressure and low temperature, began to destabilize. Methane hydrates broke down, releasing methane into the water and the atmosphere. Across the supercontinent Pangaea, the already arid interior became even more extreme. As forests collapsed, weathering rates increased, and exposed land surfaces became more vulnerable to erosion. Iron-rich red sediments appeared more frequently in the geologic record, reflecting hot, dry, and oxidizing conditions. What is most frightening is not any single factor in isolation, but the way they connected. Rising carbon dioxide led to warming. Warming also destabilized methane hydrates, further amplifying the greenhouse effect. Within roughly 60,000 years, a blink of an eye on the geologic timescale, the climate system and the biosphere were pushed into a fundamentally different state. Thresholds were crossed, and once crossed, self-amplifying processes took control, dragging the entire biosphere with them. And once the chain reaction had begun, the consequences did not stop at atmospheric or ocean chemistry. They spread into biology itself, and marine organisms were the first victims of a system that had moved beyond its limits. When the climate system crossed its threshold, the first place to bear the consequences was the ocean. Around 252 million years ago, during the Permian-Triassic extinction event, Earth's oceans became the primary battlefield of an unprecedented biological crisis. Estimates based on the fossil record suggest that 81% of marine genera disappeared, the highest extinction level in the entire history of complex life. Before the crisis, the Permian seas were rich ecosystems. Trilobites, arthropods that had existed for more than 270 million years, were still present, and brachiopods blanketed the shallow seafloor. Seawater temperatures rose sharply, Paleoclimate models and oxygen isotope data from fossils indicate that ocean surface temperatures may have increased by 8 to 10 degrees Celsius. Anoxia spread, first through the deep waters, then gradually into the shallows. Evidence from deep sea sediments reveals the expansion of global-scale dead zones. Trilobites, one of the most ancient groups of organisms, vanished completely after this event. Eurypterids, the giant sea scorpions, never returned. Blastoids, acanthodians, and many early cartilaginous fish groups were erased from evolutionary history. Alongside oxygen loss came ocean acidification. Carbon dioxide dissolved into seawater, forming carbonic acid and lowering ocean pH. Organisms with calcium carbonate shells, such as brachiopods and many ancient corals, struggled to maintain their skeletal structures. When carbonate saturation dropped below stable thresholds, their shells became prone to dissolution or failed to form properly. Another factor worsened the situation: eutenia, the buildup of hydrogen sulfide in the water column. Hydrogen sulfide is not only toxic to marine life, it can also escape into the atmosphere, affecting terrestrial organisms. Notably, extinction did not strike all environments simultaneously. Shallow marine ecosystems, particularly in tropical regions, were hit the hardest. Survivors tended to be organisms capable of enduring extreme conditions. Small in size, metabolically flexible, and tolerant of low oxygen environments. Ammonites, though heavily impacted, retained a few surviving lineages and later rapidly diversified during the Triassic. Trilobites, by contrast, disappeared forever after more than 270 million years of dominance. Stratigraphic studies indicate that it took approximately 5 to 10 million years for marine biodiversity to begin a basic recovery. And when the seas collapse, the continents cannot endure for long. We now leave the water and step onto the supercontinent Pangaea, where interior temperatures may have exceeded 50 degrees Celsius and forest ecosystems began to disintegrate. Around 252 million years ago, across the vast supercontinent of Pangaea, another crisis was quietly unfolding. There were no global tsunamis, no colossal impact crater, only steadily rising temperatures, a shifting atmosphere, and terrestrial ecosystems pushed to the limits of survival. The fossil record shows that roughly 70% of terrestrial vertebrate species vanished during the Permian Triassic event. As carbon dioxide from the eruptions of the Siberian traps poured into the atmosphere, the greenhouse effect intensified. Paleoclimate models and oxygen isotope analyses from sediments indicate that global average temperatures rose by about 8 to 10 degrees Celsius. Paleoclimate research suggests that summer temperatures inland may have exceeded 45 degrees Celsius, even approaching or surpassing 50 degrees Celsius in some tropical regions. Stratigraphic records reveal a coal gap, a span of several million years in the early Triassic, during which almost no new coal deposits formed. Coal is the product of humid forested swamps, where plant material accumulates and is buried in oxygen-poor environments. Its disappearance signals that these wet forest ecosystems either declined severely or vanished entirely during this period. Without dense vegetation cover, bare soils were exposed, and iron-rich red sediments became common in early Triassic geological records. The continents shifted from the green of forests to the red of arid, sun-scorched land. Herbivores lost their food sources, carnivores lost their prey, and terrestrial food webs fractured in a pattern eerily similar to the oceans. Gorgonopsids, the apex predators of the late Permian, went extinct. Dinocephalians, Scutosaurus, and many other lineages failed to cross the Permian-Triassic boundary. Some modeling studies suggest that oxygen levels may have dropped significantly after the event, making it harder for large animals to respire efficiently. In a hot, oxygen-poor world, large body size became a physiological disadvantage. The result was that early Triassic ecosystems were simplified and impoverished, pointing to a destabilized system in which only a few species capable of enduring extreme conditions could survive and temporarily dominate. The continents were overheated because ecological systems could no longer regulate themselves. As forests vanished, the terrestrial carbon cycle was disrupted. As soils eroded, nutrients washed into the oceans, further intensifying marine anoxia. But to truly understand how fragile that system had become, we must look back to the time before collapse. What did Pangaea look like before the catastrophe? What ecosystems once thrived when the world was still in balance? Before life was erased on an unprecedented scale, late Permian Earth was a complex, diverse world that seemed stable. If you had stood on the surface of the planet around 255 to 260 million years ago, you would have seen no sign that 90% of life was about to vanish. Nearly all land masses had fused into a single supercontinent. Pangaea stretched from the southern polar regions toward the northern high latitudes. encircled by the vast Panthalassa Ocean and a great inland sea known as Tethys to the east. The concentration of continental mass made the interior of Pangaea arid, with extreme swings between day and night and between seasons. Yet along the coasts and margins, rich ecosystems still flourished. On land, therapsids, mammal-like reptiles, dominated the ecosystems, including gorgonopsids, apex predators armed with dagger-like canine teeth. They hunted dicynodonts, herbivores with beaked mouths, sturdy bodies, and sizes that could rival a small cow. Dinocephalians, large-bodied animals with thick skulls, had once been major components of these ecosystems before gradually declining. Terrestrial ecosystems were not defined by large animals alone. Gymnosperms, such as primitive conifers and seed ferns, were dominant plant groups. Scattered forests provided shelter for diverse insects and small vertebrates. And despite the arid interior, river valleys and floodplains still sustained abundant life. Beneath the waves, trilobites, arthropods that had endured for more than 270 million years, were still present, though diminished from their peak diversity. While brachiopods, ammonites, and numerous other mollusks formed dense reef communities. Ancient sharks such as Helicoprion, estimated at 5 to 8 meters long and known for their distinctive spiral tooth structure, cruised through shallow seas. Here, bottom dwellers, planktonic organisms, and predators together formed stable food webs. Climate models suggest that Pangaea's vast interior remained arid, while coastal regions and higher latitudes maintained more temperate conditions. So what made this world fragile? The stability of ecosystems depends on a balance among climate, the carbon cycle, and the availability of habitats. As shallow continental shelves contracted, marine communities became more concentrated and potentially more vulnerable to disruption. Specialization maximizes survival under stable conditions, yet it reduces flexibility when environments shift rapidly. By the late Permian, biodiversity remained high. But the structure of ecosystems may already have lost some resilience. As shallow seas diminished and seasonal climate swings intensified across Pangaea, the system began to experience mounting stress. An ecosystem that has remained stable and diverse for tens of millions of years can still collapse if pushed beyond a threshold it cannot regulate. And once that threshold is crossed, how quickly can a global biological shock unfold? On Earth's timescale, this collapse happened almost in the blink of an eye. Uranium lead isotope analyses of zircon from volcanic ash layers at the Permian Triassic boundary suggest that the primary extinction event may have lasted around 60,000 years. A long time to sound human, but on the geological scale, where an epoch can last tens of millions of years, it was a sudden shock. Stratigraphic and fossil studies suggest that marine decline stretched across roughly 200,000 years, with the peak of extinction concentrated within a brief interval at the Permian Triassic boundary. In the oceans, reef communities and benthic organisms disappeared nearly simultaneously across multiple regions. The breakdown of food webs was not merely the loss of individual species, but the loss of entire ecological structures. When primary producers declined, higher-level consumers rapidly lost their food sources. This was not a slow fade. It was a domino effect on a global scale. On land, faunal turnover is clearly documented by the transition from diverse communities to low-diversity assemblages often dominated by just a few surviving species. At some early Triassic sites, fossils of Lystrosaurus account for approximately 90 to 96% of specimens discovered. An ecosystem in which nearly a single species dominates is not a healthy one. It signals profound imbalance. Notably, the total duration of ecological upheaval, from the onset of decline to the establishment of a new equilibrium, lasted around 1 million years. Across Earth's 4.54 billion year history, 1 million years represents only about 0.02%. If Earth's history were compressed into a single calendar year, the entire Permian Triassic shock would unfold in less than the final 2 hours of December 31. Fossil evidence shows not only a dramatic reduction in species numbers, but also the collapse of ecological complexity. Before the extinction, marine ecosystems contained multiple trophic levels and intricate networks of interaction. Afterward, these structures were simplified with fewer layers and fewer connections. That simplification was a direct consequence of the speed of collapse. Did life rebound quickly and with force, or did Earth enter a prolonged phase of stagnation? Permian Triassic nightmare finally passed, Earth did not immediately spring back to life. Instead, it entered a world that was empty, silent, and biologically impoverished for far longer than anyone might have imagined. Stratigraphic studies show that it took roughly 5 to 10 million years after the Permian-Triassic boundary for marine ecosystems to begin recovering at even a basic level. In the early Triassic oceans, coral reefs, once the epicenters of biodiversity, had nearly vanished. It was not until the Middle Triassic, more than 5 million years after the catastrophe, that reef ecosystems began to reappear with relatively stable structures. Chemical evidence preserved in marine sediments reveals that oceanic oxygen depletion and chemical instability persisted for millions of years into the early Triassic. On land, the picture was no brighter in regions such as South Africa and China. Early Triassic fossil records show the near total dominance of a few opportunistic species. Lystrosaurus, a medium-sized herbivorous therapsid, at some sites accounts for approximately 90 to 96% of all vertebrate fossils found in early Triassic strata. Quantitative studies of biodiversity indicate that the full recovery of terrestrial vertebrates may have taken up to about 30 million years, well into the Middle Triassic. Why was recovery so slow? The scale of loss was overwhelming. When approximately 81 to 96% of marine species and around 70% of terrestrial vertebrates disappeared, most ecological relationships vanished with them. An ecosystem is not merely a collection of species, it is a web of interactions. Second, the post-extinction environment remained unstable. When only a few species dominate, competitive pressure decreases, and the pace of evolutionary innovation can slow. If we compress those 30 million years of recovery into the span of a human lifetime, it would be like spending decades rebuilding an ecosystem that had been destroyed in a matter of minutes. Throughout this prolonged aftermath, many regions of Earth were characterized by what scientists call disaster faunas. Low-diversity communities composed of hardy, generalist organisms with little specialization. How did those emerging evolutionary branches go on to reshape the planet? Paving the way for an entirely different era, the age of diapsid reptiles, and eventually the rise of the dinosaurs. After the greatest collapse in the history of life, Earth did not simply recover, it reorganized. Before the Permian, many terrestrial ecosystems were dominated by therapsids. Mammal-like reptiles, that included dicynodonts, gorgonopsids, and dinocephalians. But after the extinction, most of those branches were gone. Only a small number survived the Permian-Triassic boundary, and even they declined rapidly in the early Triassic. In that vacuum, another group began to rise, the diapsids, a lineage of reptiles distinguished by two temporal openings behind the eye socket in the skull. A subtle anatomical feature with profound biological significance. This structure allowed stronger muscle attachment, producing more powerful and flexible biting. From that anatomical foundation, diapsids gradually diversified into multiple evolutionary branches. By the Middle Triassic, around 240 to 230 million years ago, several diapsid lineages had developed into groups occupying clearly defined ecological roles. On land, archosaurs, a major branch of diapsids, began filling the ecological niches of medium and large-sized herbivores and predators. In river systems and wetlands, phytosaurs emerged. They had elongated bodies and narrow snouts, resembling modern crocodiles, though they were not direct ancestors of today's crocodilians. Some species exceeded 5 meters in length. They occupied the role of apex predators in freshwater ecosystems. In the oceans, other diapsid branches evolved into marine reptiles. Ichthyosaurs appeared early in the Triassic, with streamlined bodies, developed fins, and crescent-shaped tails, fully adapted to marine life. Some ichthyosaurs grew beyond 10 meters in length. They filled the vacant roles once held by Permian marine predators. Ecological roles: apex predators, large herbivores, fast-moving marine hunters, were being reoccupied by entirely new evolutionary lineages. No trilobites, no eurypterids, no dominant therapsid lineages shaping ecosystems. Instead, a world increasingly defined by archosaurs, marine reptiles, and other diapsid branches. By the late Triassic, around 230 to 220 million years ago, the first dinosaurs emerged from within the archosaur lineage. And when we trace the climatic chain of events that led to this transformation, rising carbon dioxide, warming, oxygen loss, ecological collapse, an unavoidable question emerges. If Earth's system once crossed such a threshold in the deep past, what prevents it from crossing that threshold again? The Permian extinction event stands as the most brutal demonstration of how fragile the biosphere can be when confronted with extreme geological upheaval. When the Siberian eruption released massive amounts of greenhouse gases, it not only triggered a chain reaction of ecological collapse from ocean to land, but also pushed life to the brink of complete extinction. Yet within the suffocating stillness of a planet choked by heat and acidifying oceans, what scientists now call the Great Dying also functioned as a harsh but necessary evolutionary filter. By disrupting the old order, this catastrophe made way for new, more adaptable and flexible biological structures, laying the foundation for the rise of the Triassic period and the subsequent age of dinosaurs. Once the balance is broken, the history of life could be completely rewritten in the blink of an eye in geological time.
This macro shot reveals the final stages of desiccation, a stark reminder of
We are witnessing a systemic collapse.
The creature's labored breathing and weakened movement are clear indicators of biological collapse.
The Permian period. Here, in the dense, oxygen-rich swamps, we find the bizarre Diplocaulus,